Hi everyone, this is Maverick Paul, the chemistry guru. Now in this video, we want to discuss how to determine the major product for electrophilic addition of propene. So let's take a look at this question. When propene reacts with iodine monobromide, IBR, in the presence of concentrated aqueous sodium nitrate, a mixture of products is obtained. So question is asking which of the following is a possible major product formed in this reaction. Now, we should recognize that these reagents and conditions involving IBR in the presence of concentrated aqueous sodium nitrate is not in syllabus. So therefore, what we have to do is we have to use the mechanism of alkene to deduce the products that is formed and of course determine which one is the major product. So this is actually an application question involving electrophilic addition mechanism. Now, if I consider electrophilic addition mechanism for alkenes, we understand that in the first step, your electrophile is involved and it joins to my alkene and we form a carbocation. So the first thing we have to deduce is based on the reactants that we have involving IBR and concentrated aqueous sodium nitrate, which are all the species that are present, and we want to deduce the possible electrophile in step number 1. So the idea is here. Maybe let's take a look at it. First thing we have to determine is the electrophile, because the electrophile is involved in the first step. So we have IBR, we have concentrated sodium nitrate, that means IBR is present. We have Na+, we have NO3-, and we also have water. Since this is concentrated, so water is present. Involving electrophile, we do understand that electrophile, it has to be either positively charged or partial positive charge. And if I consider IBR, because bromine is more electronegative than iodine, so the charge on my iodine will be a partial plus. Bromine is a partial minus charge, so iodine can function as an electrophile. Of course, Br, since it is a partial minus charge, cannot function as electrophile, since it is electron rich. Involving Na+, it is positively charged, but Na+ is very stable, so it doesn't function as an electrophile. We will ignore Na+. Involving nitrate, this is negatively charged, cannot function as an electrophile. Again, electrophile has to be partial positive or positive charge, because electrophile is counted as an electron deficient species. Alright, involving water, oxygen in water is a partial minus charge. Oxygen cannot be an electrophile. Hydrogen in water, it is a partial positive charge, but hydrogen in water is fairly stable. So again, it wouldn't function as an electrophile. So therefore, the only species that can function as an electrophile in this sample involving IBR, concentrated NaNO3, the only electrophile will be iodine. And therefore, we should be able to draw out the mechanism involving the first step where my alkene carbon attacks the iodine, which is partial positive charge, and you break the IBR bond and both electrons go to Br, we form a bromide anion. Iodine will join to my alkene carbon. Now, if I consider propene, since both of my alkene carbons are different, if I number carbon position 1 and carbon position 2, you notice carbon position 1 is attached to 2 hydrogen, carbon position 2 is attached to 1 hydrogen and 1 methyl group. So where the iodine goes to, whether it is joined to carbon 1 or it joins to carbon 2, I'll have 2 different carbocations that can be formed, and one of them is actually more stable and therefore it will be more likely formed. That guy will give me the major product. So what we will do is we will focus on drawing the major product. And if I want to very quickly determine which carbocation is more stable, we can actually use modified Markovnikov rule, which is a variation or more general Markovnikov rule. Remember, Markovnikov says that when we are doing electrophilic addition reactions and when we're adding species like HBr, HCl, HOH, which is water, hydrogen will join to the carbon with more hydrogen to give me the major product. Now, modified Markovnikov rule says that the electrophile will join to the carbon with more hydrogen to give me the major product. So if I look at my iodine, which is the electrophile here, carbon number 1 has 2 hydrogen, carbon number 2 only has 1 hydrogen. So according to modified Markovnikov rule, your iodine will join to carbon position 1. So the C+ will be on carbon position 2. This guy eventually will give me the major product. Now again, this is the major species that can be formed because it is more stable. It is still possible for iodine to join to carbon position 2 where the carbon has less hydrogen, but that guy is going to be the minor product. We can also draw out that intermediate that is formed. So I can have a CH3, then I can have my hydrogen here. Iodine joins to carbon position 2, then I'll end up with your carbocation on carbon position 1. So it is still possible for me to form this carbocation, but this guy is less stable, less likely formed. Eventually this will give me the minor product. So first thing we've determined is the most likely carbocation form will be this. Iodine joined to carbon position 1, then the C plus is on carbon position 2. Now the next thing we have to do is we have to consider the second step, which are all the nucleophiles that can come in and attack my C plus. Because my carbocation is positively charged, so in the second step, it would attract the negative species and it will attract all the possible nucleophiles that we have. So we are able to determine what are the nucleophiles in the second step. You notice if I have a carbocation here, which is positively charged, which are all the negative things that is remaining in the reaction mixture that can join to your C+. I can have Br-, which is formed at the end of the first step. This bromide comes from IBr. I have nitrate, which comes from concentrated sodium nitrate, obviously. We also have OH- that comes from water. Actually, water is the one that goes in, then later undergoes deprotonation, but we can just view this as OH- from water. So therefore, it is possible for me to add iodine and bromine to my alkene, which is this guy here. Possible for me to add iodine nitrate, which is this species here. Possible for me to add iodine and OH, which is this species here. So all these products are possible if this is my carbocation. Now the next thing we can also deduce is which is the nucleophile that is more likely to attack my carbocation. Because the question did give us this information, it says that your sodium nitrate, it is concentrated. So concentration for your nitrate should be significantly higher as compared to the rest of the species. Higher probability for your NO3- to attack your C+. So we would expect the major species to be the first guy that we draw here. I would expect the major species to be iodine attached to position 1. Then your nitrate ONO2 to be attached to carbon position 2. So this guy should be my major product. And essentially we have already figured out what is the major species that is formed, and therefore we can look through the options. C will be the answer, which is the major product that we have deduced previously. I think it is also a good idea to look through the rest of the options, see whether will they be considered as the minor product, or whether is it possible for me to form all these species in the first place. Now involving A, where I add iodine to carbon position 2 and bromine to carbon position 1. Now actually this is possible, but it is the minor product. If you recall, what we have considered previously is when your iodine joins to my carbon, the major product will be iodine joined to carbon position 1. Now the minor product will be iodine joined to carbon position 2, and I have a carbocation to carbon position 1. Then my Br- can join to my C+ at carbon position 1. Then I'll end up with your compound A. So iodine joined to carbon 2, bromine joined to carbon 1. This is your compound A. It is possible for me to form this guy, but this will be the minor product because the carbocation is less stable, less likely formed. Now involving B, it is not possible for me to form compound B because both your OH group, it is a nucleophile, and your bromide, it is also a nucleophile. So there's no way for me to add two negative species to my alkene. Remember, electrophilic addition of alkene, step number 1 must involve an electrophile, which is a positive guy. Step number 2 must involve a nucleophile, which is a minus guy. The two groups that I'm adding to alkene must be a plus and a minus. So you notice A is a plus and a minus, C is a plus and a minus. Then all these products that we've deduced previously is all plus and minus. Iodine is a plus, NO3 is a minus, iodine is a plus, Br is a minus, iodine is a plus, OH is a minus. The two groups I'm adding to alkene must be 1 plus and 1 minus. The plus is the electrophile that goes in the first step. The minus is the nucleophile that goes in the second step. So it is not possible for me to form B because it is adding a minus minus. This guy, it is not formed at all. Involving D, this product is also not formed because Na plus is super stable. Na plus will not take part in reaction. So it is not possible for me to form a carbon-sodium covalent bond. So D is also not formed. So hopefully we notice that in order for us to deduce the products that can be formed, if you are given reagents and conditions that is not in syllabus, and therefore we have to do application, what can we use to deduce the products that are being formed, even to the extent of being able to determine which is the major minor product, we actually need to make use of the mechanism. So for your electrophilic addition of propene, you can make use of the understanding of your mechanism to deduce the major product for this question. Alright, so that was the discussion involving deducing the major product for electrophilic addition of propene. And if you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. I'll see you next week.